Now, what is the activation energy? This is one of the topics that we're going to talk about in this video, as well as the temperature and rate and the Arrhenius equation. So let's start by the activation energy. Activation energy is the minimum amount of energy that is needed for the reaction to occur. If I want to give you a visualization for it, a graph like this would be best. So we have energy on the y-axis and progress on the x-axis. The graph would be something like this. These are our reactants over here. We call them reactants. And we have our product here. Notice that after we get our product from the reactants, the energy has been lowered. And the distance from here to there is the activation energy required. So now, the higher the activation energy, the slower the rate of reaction, because more energy is needed to convert reactants into the products. So what I'm like, the way that we can get it, like without even like trying to memorize it, think about a hill. A person trying to move a cart in a hill. We have a graph like this, and also we have a hill like this. And so now, will it be easier for a person to move his cart from here in graph A, or will it be easier for that person to move his cart to this point using this hill? Of course, this one would be easier. So now, which one would be the faster? Like, which one do you think does take longer to reach the destination point, which is here? Obviously, this one would be faster, much faster than this one. So what we drive is, so the point from there to there is the activation energy. We can show them as EA. And also here is the activation energy required. So the higher the activation energy, the slower the rate of reaction. So this one has a slower rate of reaction. This one is a higher and faster rate of reaction. Rate of reaction. And this one has a low activation energy. This one has high activation energy. Notice that that's important, and you can just think about it. And there are also some factors that affect the activation energy. We are going to talk about 4 of them: the nature of the reactants, the concentration of the reactants, the temperature, and the presence of catalysts. So let's start by the nature of the reactants. Consider sodium and water. The rate of chemical reaction also depends on the nature of the participating reactants molecule. If we consider the sodium, when we put it on the water, like the rate of reaction is so fast, it happens in a blink of an eye. Like it might take at best like maybe 2 seconds, 3 seconds. It won't take minutes, it won't take days. It's like rusting happens. It won't take months, it won't take years. It just happens so fast that it shows one of the factors that can affect the activation energy. And this one shows that the activation energy it's much lower in comparison to the other reaction, even like if there is any activation energy for it. And the other thing is the concentration. Increasing the concentration of the reactants increase the rate of reaction and thus lower the activation energy. Greater concentration means more reactant molecules, which leads to a greater number of collisions. So another, like if you want to draw it, it would be something like this. Imagine we have two boxes and there's only like 1, 2, 1, 2, 1, 2, 4, and this box 1, 2, 3, 4, 5, 6, 7, 8, 9. So now, this one has low concentration. This one has high concentration. So, which one do you think would have a higher rate of collision? Obviously this one, because there is more reactants in here. So the chance of, this is just a statistic and probability. Imagine you're in a crowded room which there's only like 8 people in it, and I will tell those person to run. Like, what's the chance of those people to collide with each other? And we have a room of 18 people here. So and I would tell them to run. So what's the probability of these people, like this class, would collide with each other? And you would obviously go for the 18 one and it shows that the higher the concentration, the higher the chance of collision, which increases, which lowers the activation energy. And the orientation effects on the reaction rate, again. In addition to there being minimum energy requirement necessary for the reaction, there are also orientation requirements. So for example, we have a molecule like this. It's a bit hard to draw. And it would produce like 2 of these big parts and okay, like this. So if I want to show it, like how does the orientation affect? If one faces like this and the other faces like this, no collision. It's an ineffective collision, because what we are trying to get is 2 of these big guys and separate them. So for example, this one is NOCl plus. NOCl produces 2NO plus Cl2. So now we want to produce Cl2. These cannot produce Cl2 because Cl2 is the one that is going to like collide with each other and it would be effective. Again, we have an OCl, but here this time, let me just show it like this to be different. It's like this, but again, we have a Cl here. The big ones are Cl, and the other 2, and an O. So now, do you think there will be a collision here? Like, will we produce Cl2? No. So these are ineffective collisions. Ineffective collisions. But what if Cl combines to each other? Yes, this is an effective collisions. And we will going to produce a Cl2 here. So notice that the orientation do play its part on that lowering or increasing the activation energy. And also the temperature. The temperature is a measure of average kinetic energy of a molecule. And if you remember, the kinetic energy can be calculated by half mass V squared. which is its speed. Increasing the temperature increases. So if we increase the temperature, the average kinetic energy will increases. The V speed increases. So the number of effective collisions increases too. The collisions that lead to a reaction. And that's a basic one. A greater number of collision increases the rate of the reaction and lowers the activation energy, as we talked about. So now we also have a catalyst that has an effect on activation energy. A catalyst is a substance that is added to a reaction to increase the rate of reaction by lowering the activation energy. So what catalyst does, let's imagine that's our reactants. These are reactants, this part. And that's how the graph will look, this one, and this is our product, reactants, products. This is how the without catalyst graph looks like. This is energy here, and this is progress, right? Notice that the activation energy is high. But if we add catalyst, the new reaction would be, for example, the new activation energy for the reaction will be like this. Notice that the activation energy has changed. And a catalyst, it's important to know that a catalyst does not affect the energies of the reactants and products. So these are constant. The energy of the reactants and the products are constant. It just lowers the activation energy. And a catalyst is not used up when added to a chemical reaction, but regenerated after the completion of the reaction. So, for example, A plus B produces a product, AB. And this is an uncatalyzed reaction. Uncatalyzed reaction. But here, we also have A plus B produces plus catalyst produces AB plus catalyst. Notice that there is no consumption of the catalyst in a reaction. This is a catalyzed reaction. So now we go for the Arrhenius equation. It shows the effect of temperature on the rate of reaction. So, and that's it. So the reaction and the equation will be like this. K, it's important, A times E with the power of negative EA over RT. So what is K? K is rate constant. What is A? A is pre-exponential factor. They will usually give you this on your exams. Because it is determined empirically and describes the frequency of the collision between the reactant molecules, so you cannot calculate it. It's something that happens during an experiment, so you're not responsible to memorize it or trying to find a formula for it. They will give you the answer for it, the value for it. EA is our activation energy. R is our ideal gas constant, which if we try to use like kelvins, mole, and joules, then that number is 8.13314 joule per mole Kelvin. And T is the temperature. And notice It's in Kelvin. It's important to know that. So, from the Arrhenius equation, if we take the natural logarithm of both sides, we get the idea of ln k equals to the ln a negative minus ea over rt. And that's what we get if we take the ln of it. We can prove this point mathematically, but if we like try to use the 2 points like k rate 1 and rate 2, it is shown that we don't need a in a question. So if we try to use 2.4, it would be, this one is for a single point and this one is for 2.4. That would be a ln of k2 over k1 equals to negative ea over r 1 over t2 minus 1 over t1. Again, they will give you this, but if you want to do it mathematically, just consider, I can show it mathematically. So let's say ln, I would write it down. I mean, I'm doing it because they might don't give you that, and then you just have to calculate it. So ln k equals to ln a, I'm not using the minus activation energy over RT. So now if you have 2 points, so this one for 1 T1, it would give us ln k2 equals to ln a2 minus a. A is similar. A is like a constant. It happens during an experiment, and we just have to find it empirically. And 8RT2. So if we divide these two by each other, so ln minus ln k1, we can show it like this. It's better, like it would be easier. Ln k1 minus, we're going that one in that form to the left side, ln a equals to negative ea rt, and then we say ln k2 over a equals to negative ea rt1. For here, we can again say the same thing, ln k2 minus ln a equals to negative ea over rt, which concludes that ln this one is ln a k1, k1, ln k2 over a equals to negative ea rt2. And now if we subtract them like this one by this, it would be ln k2 minus over a minus ln k1 over a equals to negative ea rt2 minus negative ea rt1. And then you just have to say again, using that natural logarithm rule, this one k2 over a, k1 over a, then the negative ea over r is a constant, so negative ea over r is here, and then we say, okay, 1 over t2 minus 1 over t1, and then so these will cancel each other's out, so the total equation will look like this. Ln K2 or K1 equals to negative EA activation energy over R times 1 over T2 minus 1 over T1. So now, I will give you an example for this. Try to pause the video and solve it. Then check your answer with the answer that I got. So now pause the video and try to solve it. Then check your answer with the answer that I got. So it's just the gas phase, the gas phase decomposition of HI and into H2 and I2 iodide is found to have an activation energy of 75.5 kilojoules per mole. The rate constant at 20 Celsius is 2.75 times to the 10 with the power of negative 2. What is the value of K at 60 Celsius? So we have T1. T1 is 20 plus 273.15. That's how we convert the Celsius into Kelvin. And we have again T2, which will be 60 plus 273.15, and this one is 293.15. This one will give in 333.15. Now, what else do we have? The rate constant at 20 Celsius is K1. It's our K1 is 2.75 times to the power of negative 2, and we want the K2. Using the formula which we have, ln K2 over K1 equals to activation energy over R over T times 1 over T2, 1 over T1, and it putting our values, ln of K2 over 2.75 times to the 10 with the power of negative 2 equals to negative, what was the activation energy? 70.5 kilojoules. 75.5 times to the 10 with the power of 3 over our R is 8.314 and times to the 1 over 33.15 minus 1 over 293 over 15. So the Ka, like the K2, sorry, would be would be would be 1.14, and that's basically our K2, which is much higher than the first one, K1. And I want you guys to think about it. Does it make any sense, the number that we got? Yes. And why? Because we increased the temperature by 40 degrees Celsius, right? And we said the temperature almost every time have a positive effect of the rate on the activation energy. It lowers the activation energy by increasing the rate constant. Now here, as we can see, the rate constant have increased by much. It's 1.14, and for the example, and at the 20 degrees Celsius was 2.75 times to the 10 to the power of negative 2, which is much lower than the actual one. So I can give you guys another example. Yes, we can do another. So now that's our example on, that's our last example, basically. So it says rate constant for reaction for determined to be 3.7 times to the 10 to the power of -5 at 25 Celsius, and 1.7 times to the 10 with the power of -3 at 55 Celsius. Calculate the activation energy for this reaction in the unit of kilojoules per mole. So using the formula that we derived from the Arrhenius equation, ln of K2 over K1 equals to the negative EA over R 1 T2 minus T1 over T1. And if you want to just calculate the negative EA, not negative, the EA, we have to make it alone. So by doing that, we can say the ln of, like here, divided by this number and multiply by that number, R. So we can say ln of K2 over K1 multiply by R over 1 over T2 minus 1 over T1. Okay, what is our T1? T1, that's the formula that we will use. T1 is 25. Let's just consider 273, which is 298 Kelvin. T2 is 55 plus 273. That'll be 8, 12, okay, 328 Kelvin. So now we just put our values in the formula, and EA will be ln of, what is K2? 1.7 times to the 10 to the power of -3 over 3.7 times to the 10 to the power of -3 over times R, which is 8.314 over 1 over 328 Kelvin minus 1 over 298 Kelvin, which will give an answer of a value of which will give us the value of 1.0 times to the 10 to the power of 3 joule per mole. So the activation energy, oh, I'm sorry, this is 5. 10 to the power of, why did I put negative here? 5. So the activation energy is 100 or 100, not just 100 kilojoules per mole. And that was our last example. If you guys have any other questions that you are stuck on, you can ask me, or if anything that was questionable in the video, you can ask me in the comment section. I would be more than happy to answer that. I hope you guys have a great day. Thank you for watching my video. Please subscribe and like. Have a nice day.